All right, so we're going to talk about measuring things in science. And when we're talking about measuring things in science, pretty much all scientists use a system of measurement called the SI system. And it's related to what we used to call the metric system. First of all, does anybody know what SI stands for? It actually stands for International System of Units. So why is it SI and not IS? The French came up with it. And if you've ever taken French, they write everything backward from us, right? Instead of saying international system, they say System International. Backwards. It's one of the few good things the French have ever done. Their system is much, much better than our system. Think about it for a second. I'm just going to ask you some random questions. Hold up your hand if you're sure you know the answer about our system of measurement. Systems of measurement that you've been using for 14 years or so. You should know these things, but I'm going to bet you don't. How many know how many feet are in a mile? Hold up your hand if you know how many feet are in a mile. It's something you ought to think you ought to know, all right? Most of you probably don't. All right, somebody tell me who knows. Anybody?
I think it's like
5,280 feet in a mile. A lot of you probably didn't know that. How many of you, hold up your hand if you know, how many teaspoons are in a tablespoon? How many teaspoons are in, hold up if you're sure you know, how many teaspoons are in a tablespoon? All right, we have two hands. Let's see if you know. What do you think? Nope. Nope. So nobody in here knew for sure. 3. That's stuff people use all the time to like cook and stuff. Let's go. It's real simple. How many of you know for sure how many ounces are in a pound? Ounces in a pound. All right, I'm seeing 3 hands. What do you think? 16. So we have 1 or 2, 3 maybe. Those are things that you would think we ought to know, right? But people don't know because our system is just a random assortment of junk all thrown together. That's not the way the metric system is. But let me go back a second. Other than the United States, who else in the world uses our system of measurement? It's called the English system of measurement, but England doesn't even use it anymore. There's one other place that I know of, one other country, and it's in the news right now, this other country. Europe. No? Europe. There's a place called Liberia. Why is Liberia in the news right now? That's where Ebola is happening right now. Okay? But let's think for a second. Why would a little bitty country in Africa be using the same system of measurement that we're using? And it be the only other place? Okay. How? A little history lesson here for free. Let me give you a clue about Liberia. The capital of the country of Liberia is Monrovia. Anybody know who that might be named after?
Marilyn Monroe.
Not Marilyn Monroe. President of the United States, James Monroe. Any idea why? Nope. When James Monroe was president, there was a move to free some slaves. Now, James Monroe was one of the early presidents, right? He was like 5th, I think. So that's very early in the history of the country. There's a movement to free slaves. And what happened to a lot of those slaves that were freed back in that time? They were sent back to Africa. And in particular, they were sent to this little place called Liberia. So we started it as a place to send freed slaves. Even today, Liberia's flag looks almost just like ours. It has less stars and less stripes. It looks like our flag. They use our system of measurement. Their capital is named after a U.S. president. Turns out they're not very pro-American anymore, but they still have a lot of American themes over there. But other than that, pretty much every civilized country in the world uses the metric system. And the reason they use the metric system is because it's better and it's easier. It's much easier to remember things and know things and be accurate with things. That's why, when I was a kid, if you went to the grocery store to buy a big bottle of Coke, what did you get? When I was a real small kid, what do you think you got? Yeah, you wouldn't have been born then. You got it in a gallon, like milk. You bought it just like milk, okay? But eventually Coke became a worldwide company, right? And they're saying, hey, we don't just sell things in the United States. We sell it in England and France and Germany and places in Africa. And they don't have a clue what a gallon is over there. So guess what? We're going to sell them liters because they know what those are. In America, y'all can figure it out. Y'all can know smart. So they switched over to 2 and 3 liter bottles. And that's happened a little bit. They tried to sneak it in, notice here and there, but we still stuck with gallons and feet. And there was a move by Congress back when I was a kid that we were going to switch over to the metric system. Congress voted. We were going to switch. All the speed limit signs were going to get switched over from miles per hour to kilometers per hour at a certain date. And the date was set. I mean, it was set in stone. It was going to happen. And then what happened? Well, the people who have political power in this country are not you guys, right? Y'all don't have any political power. They're people my age or older. And back then, those people had, if they had ever had the metric system, it was when they were in high school. Did they remember it when they were 45? No, anything. We don't want to change over. This is America. We do miles per hour. Let's forget it. So eventually, Congress just gave up. And I don't think we'll change anytime soon because people are just stuck on it. And that's what they're used to, even though they don't know it. They don't know their own system of measurement. But I don't think it's going to change. But here's why the metric system's better. Number one, it's based on something. It's based on the number 10 and powers of 10, which makes it easy to deal with. That's one of the things that makes it better. It's based on tens. Number two, there are these units called the fundamental units. If you know those, and you know a system of metric prefixes, which you guys are going to have to learn if you don't already know them, you know everything that you need to know about the metric system. So you need to know the 6 or 7 basic units, and then you need to know the prefixes. If you know those things, you know everything you need to know about metrics. So these are the fundamental or basic units in the metric system. For length, for example, the basic unit's the meter. How long is a meter? Give me an English equivalent.
3 feet.
It's a little over 3 feet. This is a meter. So a meter's a little bit bigger than a yard, right? Not much bigger, but it's a little bit bigger than a yard. A little bit more than 3 feet. The unit of mass. Remember, mass is sort of a measurement of how much, what? It's not really weight. It's how much stuff, how many atoms and molecules and stuff you're made out of. And the basic unit for that is the kilogram. Why the kilogram and not the gram? Because if you look, none of the rest of these have like prefixes in front of them. Why are they using the kilogram and not just the regular gram? How big is the gram? Tiny. It's about the size of like a paper clip. And everybody decided, hey, that's just a little too small. Let's use something a little bigger. Anybody know about how big a kilogram is in the English units?
Like,
A kilogram's a little over 2 pounds. 2.2 pounds. So it's a measurable amount. Time is the same essentially as what we use. Time is measured in seconds in the metric system, just like the same seconds we use. Now, temperature in the metric system is in a thing called Kelvin. But let's say this, if you went over, like I went to Italy a few years back, went to Rome and places like that. If you're watching the news over in Italy, and they're talking about, hey, today it's going to be so-and-so degrees, what system is the weatherman talking in most of the time? They're usually talking in Celsius. But notice the fundamental unit here is Kelvin. Anybody know what the difference is between Celsius and Kelvin? You know? Well, let's put it this way. In Celsius, what's 0 mean in Celsius?
32.
Which is what? Yeah, but why did they choose 0 or 32 in Fahrenheit? What's the magic number there? What is Fahrenheit and Celsius based on? Water. It's based on water, right? 0 degrees Celsius is when water freezes. What's 100 degrees in Celsius? When water boils. Right? So Celsius is based on water. Kelvin is not. What's 0 Kelvin mean?
Absolute zero.
It means absolute zero. Which is what? You know what absolute zero is?
Nothing can move.
Yeah, it's when it's as cold as you can possibly get. There's no heat. It means movement stops. How cold is 0 Kelvin in Celsius? Anybody know how cold 0 Kelvin is in Celsius? What's the equivalent?
100 something?
It's negative 273. It's a number you ought to know, negative 273. Negative 273 Celsius is the same as 0 Kelvin. Otherwise, the temperatures are the same, the scales are the same. 1 degree in Celsius is the same size as 1 degree in Kelvin. The only difference between those two scales is what is what. What's 0 mean? In Kelvin, 0 really means what? It really means 0. You can't get any colder than that. In Celsius, 0 means what? Water freezes. Right? There's lots of things that can get colder than freezing water, right? Lots of things. So, anyway, that's the metric unit of temperature. Something you'll deal with when you get to chemistry, not much in this class. Amount of substance. You're going to hear about the mole. Anybody heard of moles before? We're not talking about the little furry animals. Okay? Not talking about them. Do I know? Yeah, we're not talking about those we're not talking about those either. Not the little spots that you get on your skin. We're not talking about those moles. Moles are units to count things. Big amounts of things. Like if I ask you how many atoms were in this big block toy, what do you think? How many atoms do you think might be in there?
6
Millions? Billions?
Probably trillions of trillions of trillions. A mole is this huge counting unit. Like I said, we won't deal with it in biology. Another one that we won't really deal with in biology is this one, the amp or ampere. It's used for measuring electrical current. You deal with that if you take a physics class. And then another one that you'll deal with if you take a physics class is a candela. That word looks an awful lot like what? Candle, because you're measuring luminous intensity, which is essentially what in more plain English. Now what about light? Yeah, how bright it is. Okay? Brightness of light. We won't really deal with that in this class though. So the ones we're going to deal with in here are from Kelvin up to meter. Okay? So this little area right in here, those are the ones we're actually going to use. Now, if I might ask you a question on the test or quiz, what's the fundamental unit of substance, and you could tell me the mole. But in terms of actually using them, those top 4 are the ones we're going to use. All right, other thing that you need to know, these metric prefixes. Now, I'm not going to require you to memorize every one of these. Here's the ones that I want you to know. Notice they're all based on powers of 10. And I'm going to draw in something that's not on this chart. I'm going to draw in a little line right through there. What does that green line represent? Look at the powers of 10. 10 to the 0, right? That's important for that to be there. What's anything raised to the 0 power? 1. It just means 1. Okay? 1. So if we're dealing with our units, and we were dealing with like meters, this would be where 1 meter would go. Okay. The prefixes that I want you guys to know are the ones I'm about to circle here. Okay. Just those in red. And you need to know what powers they represent. So let's start by going up. As we go up this chart, what happens to the size of the unit? Does it go up or down? It goes up. So, for example, deca. And you'll see deca sometimes spelled D-E-C-A. A lot of people also spell it out. A lot of books even spell it D-E-K-A. Either one's okay. I don't care which way you spell it, but it's C or K. The abbreviation for it, though, is DA. So if we were talking about a decameter, we would abbreviate that out. How would a decameter be abbreviated? D-A-M. A decagram would be D-A-G. Make sense? So deca means 10 to the first power, which is just 10. Okay. So in a decameter, there are what? 10.
Decimeter?
A decameter, there are 10 of these. 10 meters. A decameter is 10 of these. All right, a hectometer, or hecto. Hecto means 10 to the second power. 10 times 10. That's 100. So in a hectometer, there are 100 of these yardsticks, 100 or meter sticks. In a hectogram, there are 100 grams. Kilo, 10 to the third power, or 10 times 10 times 10, 1,000. So a kilometer, 1,000 meters. Kilogram, 1,000 grams. Now notice we skip a few powers here. We skip from 10 to the third all the way up to 10 to the sixth. I'm sure there are prefixes for 10 to the fourth power and 10 to the fifth power. Nobody uses those prefixes. I'm sure they exist. I don't even know what they are. Nobody ever uses them. The next power is 10 to the sixth power. 10 times itself 6 times. That's 1,000,000. 1,000,000. So a megameter is 1,000,000 meters. A megagram is 1,000,000 grams. It's a big unit. All right, now we're going to flip around and we're going to go down the scale. As we go down the scale, what happens to the size of the units? Yeah, they get smaller. And the first one of those we're going to look at is 10 to the negative 1 power. That's deci. So a decimeter is 1/10 of a meter. So if you take this meter stick and you break it into 10 parts, a decimeter is just one of those 10 parts. Deci, D-E-C-I. 1/10. 10 to the negative 1 power. Centa means 10 to the negative 2 power, or 100. 1 over 10 squared. 100. So if you took a yard or meter stick here and you divided it into 100 pieces, a centimeter is just one of those 100 pieces. If you took a gram and divided it into 100 pieces, a centigram is just one of those 100 pieces. Milli. Milli's 10 to the minus 3. So that's 1 over 1,000 is what milli means. You divide this meter stick into 1,000 pieces. A millimeter is just one of those. Divide a gram into 1,000 pieces. A milligram is just one of those. All right, again, notice that we skip some space here. We skip from minus 3 all the way down to minus 6. And again, I'm sure there are prefixes for 10 to the minus 4 and 10 to the minus 5. Nobody ever uses those. If they exist, you don't have to worry about it. The next one you need to know is micro. Now notice it's got this weird looking U symbol. And the reason they use that, and let's pay attention to this, because we've got three prefixes here that start with M. We got mega, milli, and micro. Notice for mega they use a capital M as the symbol. Milli, they use a lowercase m. So M's kind of taken. So what's that funny little symbol right there? That is called mu. M-U. And it is the Greek version of what? M. It's the Greek M. Okay? Because they ran out of M's. But it looks like a U with a little line going down on it. Yeah, an L and a T? Yeah, maybe. Maybe. The way though that you're going to see me draw a mu, I'm probably just going to look, mine's going to look like a U, like that. It's just mu. M-U. It's the Greek version of M. but it means 1/1,000,000th. So if you divided this meter stick into 1,000,000 parts, a millimeter would be one of those 1,000,000 parts, just one. So it's very tiny. When might we use micro? What kinds of things are you probably dealing with if you're talking about micrometers or micrograms or microliters? Talking about little tiny things in biology, what kind of things might you be talking about?
Cells.
What kind of cells even maybe? Like bacteria, things that are really, really tiny, maybe viruses. Really, really, really tiny stuff. All right, let's look at this. So we talked about the basic units. We talked about the meter, kilogram, the amp, Kelvin, the second. Those are our basic units. If you put some of those units together, you get what are called derived units. For example, if I drew a square up here on the board, let's make it a rectangle. Let's say that's a rectangle. It's kind of a warped rectangle, but let's say it's a rectangle. And let's say I told you this rectangle is 2 meters long and 1/2 meter tall. I said, what's the area of that rectangle? What would you guys tell me?
You do 2 times 0.5.
To find the area of something, you take length times width, right? So 2 times 0.5. What's 2 times 0.5? 1. 1 what?
Meter.
Not 1 meter. 1 meter
Squared.
squared, right? Because it's meters times meters. So whenever you run into square things, square units, that's telling you you're measuring what? What about the square? What did we just calculate? Area. On the other hand, let's say I drew a little cube up here. It's going to test my artistic abilities, if I can do it. All right, so there's a cube. And let's say I told you that cube is 2 meters long, 2 meters deep, 2 meters tall. And I said calculate the volume of that cube. How do you calculate the volume of something if it's like a cube? Length times width times height. So what is the volume of that cube? 8 meters to the third power, right? 8 meters cubed. So if you hear of cubic meters, that's a derived unit. It's a combination of more than one of those basic units. If we're measuring the density of something, what does density tell us about something? Tells us how much mass there is in each unit of what? Volume. It's mass divided by volume. That's density. Mass divided by volume. Got some demonstrations I'll show you on density later. But if you got a unit like kilograms per meter cubed, that's a mass unit, right? That's a volume unit. It's also a derived unit, because it's more than one of those other units put together. Speed, for example. Here we measure speed in miles per hour. But if you're taking a physics class or you're over in Europe, you might talk about speed in terms of meters per second. That's 2 SI units put together into one unit, right? It's a derived unit. There's lots of other units you might deal with. Units for force and pressure and energy. We're not going to deal so much with those in this class. Pretty much these up. But a derived unit is when you put more than one of those other units together into a single unit. Any of those are derived units. All right, another thing that we need to talk about is how do we measure things and get them right. And actually, before we do this, let's skip forward one slide and we'll come back to this one. Accuracy and precision. In everyday English, a lot of people use these words to mean exactly the same thing, right? You might say something's accurate, you might say it's precise. You probably mean the same thing. But in science, those two words mean different things. What does accurate mean in science? It's what it's supposed to be. It's right on. It is what it's supposed to be. What's precise mean?
Very, very. It's not exactly.
No. Hold that thought. Let me get this phone. Hello. Hey. Should we? Exactly. Poster boards and anything self-storage, whatever. You can get it if you want to. What precision means in science is that you get the same thing every time you measure something.
Square.
Again?
Square.
Well, like you're consistent. So let's say I know I have several lady friends who I know when they get on the scales at their house to weigh themselves, they set their scales back. You know, so it's not zero's not really zero. It's like -5 or -10. Okay? So that when they get on the scale, they really weigh 135. The scale says what? 125. Okay? Is that scale accurate? It is not accurate. But every time they get on there, it says 125, so it is what? It's precise. In science, we hope that our measurements are both, right? That we're not only accurate, we not only get the right thing, but we always get the right thing, right? We need to be accurate and precise. This little dartboard is supposed to show you the difference between those. This one over here on the far right, it's not accurate or precise, right? Those darts are everywhere. Somebody who doesn't play darts very often probably threw those, right? At least they all got on the board. They didn't hit the wall. These right here are what? They're precise, but they're not where you want them to be, right? They're not accurate. These are what? They're both, right? They're accurate, they're in the bullseye, and they're precise. That's the way you want to play darts, like that far left picture. So that being said, let's back up one slide.
It's accurate and not precise.
One measurement could be, a group of measurements could not be. All right, let's say that we're measuring something with this meter stick. If we want to make sure that we all get the same measurement, here are the rules that we're going to use to measure things. One of the first labs we're going to do in this class is going to be a measurement lab. You're going to be expected to measure things this way. So listen. This yardstick, or this meter stick, has marks on it for every one way. First of all, what are these 1, 2, 3, 4, 5, 6, 7, 8, 9, 10s? Those are centimeters, right? Because there's 100 of them. But then it's got 10 marks in between like 0 and 1. What is each one of those little marks? It's 1/10 of a centimeter or a millimeter. Point being, these have marks for every 1/10 of a centimeter, right? For every 1/10. That's the smallest mark. That's the first thing you want to do when you use a measuring device. Figure out what the smallest mark is. What does it stand for? On this meter stick, it's 1/10 of a centimeter. So let's say that these were the marks on our stick. So let's say this was maybe 10 centimeters. And over here is 11 centimeters. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. And those are our little 10th marks. And let's say that what we're trying to measure, we've got our yardstick right up to it. And what we're trying to measure is like right there. Following these rules, what are we going to write down as our measurement? 10. This is wait a minute. This is 10, and this is 11 right here. So this is the 10 mark. This is the 11 mark, and then there's what we're trying to measure right here in the middle. We're going to write down. This would be 10.1, 2, 3, 4, right? So we're going to write down 10.4. That's reading to our best mark, right? We got marks for that. But what's the last step say? Then estimate one additional digit. That means add one more place onto this number. So what would we say there maybe? Yeah, it's pretty close to 10.4, right? It's way closer to 10.4 than it is to what? 10.5. So we might say 10.41, 10.42. Those would be a good way to write that down. I'm going to say 10.42. So you always read to your best mark, and then you estimate one more place of 10, one more decimal place, one more digit. That, doing it this way makes it a lot more accurate than just saying 10.4, right? Because it's not 10.4. It's a little past 10.4. What if we were measuring something right here? I'm about to put in the black line on this. Let's say we were putting in something right on that line. It's right on that line. How would we write this measurement down? 1, 2, 3, 4, 5, 6, 7, 8. So it's 10.8, right? But that's just measuring to the best mark, right? We still got to do this. We got to estimate one more spot. It looks to me like it's right on 10.8, right? So how do we put that down? Hey, it's right on it. 10.80. Is 10.8 and 10.80, are those two different things?
Yeah. Well, technically no, but yes.
They are different things, because 10.8, if you measured something 10.8, think for a minute, hear me on this, because this is confusing. If somebody followed these rules and they got 10.8, what was the best mark on their measuring device? If they followed these rules and they got 10.8, what's the best mark on their measuring device? No, what was the best mark? You measure to your best mark and then you estimate one additional decimal place. So their best mark would have been right there, the ones place, right? And then they estimated the tenths place. But if somebody had this measurement, what was their best mark? Their best mark was the tenths place. And then they measured that one. If you're building a satellite to go into space, which measurement do you have more faith in? Left one or right one?
Right.
The right one, right? Because it's more accurate. Whatever they were measuring had more marks on it. You can be a whole lot more accurate. Whenever we measure things in science, you want to measure them this way. Figure out what that lowest mark is. Is it tenths? Is it hundredths? Is it just ones? Measure to that mark, and then estimate one more place past that, one more decimal place. Everybody good with that? All right, now let's get into the actual math here. Let's say that we want to do some conversions. Let me put in a new slide so we can actually write on this. Okay, so let's say that I told you that you had 25.2 centimeters. And I want you to convert that to, let's say, we want to convert it to decameters. Centimeters to decameters. You got to convert it. First thing you got to know are those prefixes. So let's put the prefixes over here on the board. We're going to draw in a line. This line is going to be 10 to the 0. What prefix means 10 to the first power? Not deci. Deca. What prefix means 10 to the second power? Hecto. 10 to the third power. Which one? Kilo. And 10 to the sixth power. Mega. All right, which one means 10 to the minus 1 power? Deci. 10 to the minus 2 power? Centa. And 10 to the minus 3 power? Milli. And finally, 10 to the minus 6 power? Micro. All right, so we'll try to do a conversion here. First thing we got to do, find our two units on there, centa and deca. Here's centa. Here's deca. Which one of those prefixes is smaller? Centa or deca? Centa, right? Centa's smaller, figure that out. And then I want you to count how many tens are between those two. How many tens are between them? So here's 1, 2, 3 tens, right? From here to here's 1, here to here's 2, and here to here's 3. 3 tens. Which one did we say is the bigger unit? Deca or centa? Deca. So we're going to write down 1 decameter. Or we're just going to write 1. Yeah, let's write decameter for right now. You always make the bigger one be 1. 1 decameter is how many centimeters according to this? 3 powers of 10, right? What is 3 powers of 10? 1,000. 10 to the 3rd power. Everybody with me on that? We found our 2 units. We figured out that deca is bigger. The one higher up on the chart is always bigger. We counted how many tens were between those two units, centa and deca. They're 3 tens. That means 10 to the 3rd power. 10 times 10 times 10, which is 1,000. That tells me that 1 decameter is 1,000 centimeters. That's going to be my conversion factor. I'm going to use that to work this problem. Here's what I'm going to do. I'm going to say 25.2 centimeters. I'm going to draw a little T-chart. We're doing something here called dimensional analysis, which when you get to chemistry, that's where you go next. Probably most of you go to chemistry next. You're going to do this every day in chemistry, one way or another. So we do this little T-chart. We put the number we're starting with right up here on the top left of the T. In these 2 boxes here and here, we're going to put in our conversion factor that we just figured out. Which piece of this conversion factor are we going to put down here on the bottom of this T? We're going to put 1,000 centimeters down here. Because what are we trying to do to centimeters? We want to convert, we want to get rid of centimeters, right? And in math, if you want to get rid of something, where's it got to be? It's got to be across from the thing you're trying to get the other thing with that same thing, right? If we put centimeters here and centimeters here, what happens? They cancel each other out. And we put what that's equal to up here on the top. Well, what's 1,000 centimeters equal to? 1 decameter. So let's put 1 decameter up here. So to get our answer now, what do we do? What do we have to do with the calculator? How do we finish this up? 25.2. What do we do with it? Divide it by, because it's the thousands on the bottom, right? So you divide everything on the bottom, you divide by. So we're just going to say 25.2 divided by 1,000. And we get 0.0252. So our answer to this problem is 0.0252 decameters. Always write your unit down with your answer. Let's try another. All right, this time let's say we had 525 what's the mg mean? Milligrams. And let's say we want to convert that to Hg. What would Hg be? Hectograms, right? All right. First of all, we have to find our 2 units over here. So here is milli, and here is hecto. What do we say we had to do next? Which one's bigger, hecto or milli? Hecto. So remember, we always write the bigger one down. We just call it 1 hectogram. And then what do we do next? Count the number of tens between them. So 1, 2, 3, 4, 5. I just counted how many tens were between those 2. So 1, 2, 3, 4, 5. What is 5 powers of 10? It'd be 10 times 10 times 10 times 10 times 10. That's 100,000. 100,000. That's telling me that 1 hectogram is 100,000 What? Milligrams. That's my conversion factor. Now I'm going to go up here and draw my little chart. A little dimensional analysis chart. What am I going to put on the bottom of my chart? What am I going to put right here? 100,000 milligrams. That's what am I trying to do to milligrams? Cancel them out. Got to put them across from each other to do that. And what do I put here on the top of my chart? 1 hectogram. What do I have to do to get an answer? Divide, because that's on the bottom. So here I'm going to say 525 divided by 100,000. And I get, now your calculator, depending on what kind of calculator, may put it in scientific notation, but this one's going to be let's see, 0.00525. And you always write your unit, which is hectograms. Everybody good with that? Say again now? What box? No, not now. Now I'll show you, actually the next problem we'll do is we'll put something there. Let's do a conversion with a derived unit. What did we say a derived unit was? What was a derived unit? That's okay. A derived unit was a unit made of more than one of those units, right? Combination. So let's say we had this. Let's say we had 25.8 centimeters per second. That's a derived unit, right? That's 2 units. What is that probably measuring? 25.28 centimeters per second. What is that telling you about something? What would centimeters per second tell you about something? Right, so it's measuring what? Speed. It's a speed measurement. Well, let's say we wanted to convert from centimeters per second. Let's say we wanted it in kilometers per hour instead. So we're trying to go from centimeters per second to kilometers per hour. Well, we've got 2 conversions we have to do, right? We have to convert centimeters to kilometers, and we have to convert seconds to hours. We're going to do it the same way. We're going to make our little chart. Just worry about one conversion at a time. Let's just do the top one first. So we're trying to take centimeters to what? Kilometers. So we've got to first figure out which one's bigger, right? Which one's bigger, centa or kilo? Kilo, it's way up here. Here's kilo, here's centa. So we're going to write 1 kilometer, because it's the bigger one. And now what do?
Count how many tenths.
Count how many tenths. 1, 2, 3, 4, 5. What do we say 5 powers of 10 is? 100,000. So 1 kilometer is 100,000 centimeters. Now we do that in our chart. What are we going to put down here on the bottom of our chart? 100,000 centimeters. 1 kilometer. So if we stop now, we divided 25.8 by 100,000. What's our unit? If we stopped right here, what units do we have?
Centimeters and kilometers.
Centimeters canceled out. So what's left? Kilometers per second. That's not what we want. We want kilometers per hour. So now we got to go a little further. How do we get seconds to hours? What you guys know is there's 60 seconds in what? Not in an hour. A minute, and there's 60 minutes in an hour, right? So we can do that in 2 steps. So let's first try to go seconds to minutes. We know that 60 seconds is 1 minute. That's a conversion factor. So what are we going to put up here on the top? We're going to put 60 seconds. Why do we have to put the seconds up here this time? We're trying to cancel out, right? And from the cancel, they have to be across from each other. So we want this to cancel with this. And what do we put down here on the bottom? 60 seconds is the same as 1 minute. If we stop now and we do the math, what unit do we have?
Minute.
Kilometers per minute, right? That's not what we want. We want kilometers per hour. So we've got to do one more step. And that one more step is to make one more little T-chart here. Now we got to go minutes to hours. So what are we going to put up here on the top?
60 minutes.
60 minutes is the same as, what do we put on the bottom? 1 hour. And we know we had to put the minutes up there because what are we trying to do to these minutes down here? Cancel them out. All right, so how do we finish this up? Everything that's on top, what do we have to do to all those numbers? Everything that's on the top of the T, what do we have to do? What do you do to numbers that are outside each other like that? Not add them up. Multiply them. Everything on top, you got to multiply. So I'm going to go to my calculator. I'm going to say 25.8 times 60 times 60. Just multiply it out. 25.8 times 60 times 60. And then what do I do with everything on the bottom? I divide by it. So I said 25.8 times 60 times 60. And then I go divided by what? 100,000. The only thing on the bottom. And I end up with 0.9288. And that's going to be kilometers over what? What's my unit? Kilometers over hours. 0.9288 kilometers per hour. So 25.8 centimeters per second is pretty whack. Pretty slow, right? 1 kilometer per hour, that's kind of moving snail speed, right? It's very slow. Yeah, it's slower than walking. Way slower than walking. Everybody okay with that? Let's do one more. This shouldn't be hard. Don't make this be hard. It should be easy.
The answer was 0.9288.
0.9288. All right, last problem for the day. Here we go. What's it for? Let's say we're doing. Let's say we're doing this. Let's say we're going 36.5 kilograms per. What's the big L stand for? Liter. That's 36.5 kilograms per liter. And we want to convert that to, let's say, centigrams per milliliter. What's that measuring? Kilograms per liter. What would that be measuring? What do kilograms measure? Not weight. Mass. And what do liters measure? Volume. So what are we measuring? Mass per volume, which is density. It's a density measurement. So, again, we pick one of these at a time, we convert it. Let's do kilograms to centigrams first. Which one's bigger, kilo or cento? Kilo. Here's kilo, here's cento. So we're going to say 1 kilogram equals, what do we got to do to get the equals part? Count the what? Count the tens. 1, 2, 3, 4, 5. 5 powers of 10, which is 100,000. 1 kilogram is the same as 100,000 centigrams. What are we going to put on the bottom of my T-chart up here? What am I going to put there? I'm using this. What part of this is going to go right here? 1 kilogram. Why do I have to put that part there? What am I trying to do? Cancel out kilograms. Those parts have to be across from each other. And then what's 1 kilogram the same as? 100,000 centigrams. That's going to go on top in this case. So we put the thing on the bottom that we want to cancel out with this thing over here with. All right, that takes care of that first part. Now we got to go liters to milliliters. On this blue chart here, where would a liter be? since it doesn't have a prefix, where do things without prefixes go? 10 to the 0, right? No prefix. This is where liters are. Here's milli down here. Which one's bigger, liter or milliliter? Liter. And we got to count the tens, right? 1, 2, 3. What's 3 powers of 10? 1,000, right? So my conversion factor here, the bigger unit is liter, so 1 liter is 1,000 milliliters. All right, we're trying to convert liters to milliliters. So what are we going to put right here on top of this T-chart?
1 liter.
1 liter. We have to put it there so it will what? Cancel. What is 1 liter the same as? 1,000 milliliters. To do my math, multiply everything on top. So I'm going to go 36.5 times 100,000. And then I'm going to do what? Divide by everything on the bottom. And the only thing on the bottom is what? Divided by 1,000. So we get 3,650. 3,650. And that is centigrams per milliliter. All right, let's go to that packet that you got from me on the first day real quick. All right, on page 7 in that packet are some conversions. This is your homework. Page 7 in this packet. Do these conversions. And I didn't get around to getting your page, what was it, page 9 questions. So I will take this up with those page 9 questions tomorrow. So page 7 from the packet, I will take up tomorrow with the page 9 questions from the book. Everybody with me on that?
Yes.
What I need from you, hear me on this, because you won't get credit if you don't do it this way. Make sure you hear me. What I need on these problems is I want to see that kind of work. I want to see your little T-chart. I want your answer, and I want you to circle it. Just saying like 18 is your answer, that's not good enough. 18, whatever it is it 18 grams? So show your work, circle your answer with a unit. Can you do what now? I'd rather you do everything on a separate piece of paper. Yeah. I'm not going to actually take this worksheet up from you. I don't need this tomorrow. I want a separate sheet of paper with your work and answers on it. All right, stay in your seat until that bell rings.